Hello friends, I'm Sarita Verma and welcome to my channel Electronics and Life Simplified. In this video, we will discuss about semiconductors, what is a semiconductor, the types of semiconductor, the process of doping and how solids are classified. So let's start. Solids are classified, as you already know, as conductors, semiconductors and insulators. Insulators are those substances which do not allow the current to flow through them. Example, wood, glass. Conductors are those substances which allow the current to easily pass through them. Example, copper, aluminum. And semiconductors have conductivity between insulators and conductors. As far as the energy band diagram is concerned, for insulators, this is the valence band, this is the conduction band. And the two are separated by a wide energy gap. This is also called the forbidden energy gap. It is around 15 electron volt. So, if an electron has to move from the valence band into the conduction band, a large amount of energy is needed. As far as conductors are concerned, they have overlapping valence band and conduction band. So a small amount of energy is sufficient to move the electrons from the valence band into the conduction band. For semiconductors, we have the valence band and the conduction band, but the energy gap, or which is also called the forbidden energy gap, is quite small compared to insulators. It is 1 electron volt. For germanium, it is 0.7 electron volts, whereas for silicon, it is 1.1 electron volt, which are the two commonly used semiconductors. So, as far as semiconductors are concerned, we can say they're crystalline solids which have electrical conductivity between conductors and insulators. At absolute zero, the valence electrons are engaged in covalent bonding, and whereas the other electrons in the other orbits, they are tightly bound to the nucleus. So no free electrons are available in the conduction band and the valence band is completely filled. As the temperature is raised, some of the covalent bonds break and free electrons are created. And these free electrons, if they are provided sufficient energy, they can move into the conduction band and contribute to the flow of electrons, which is nothing but current. So indirectly we can say conductivity of semiconductor increases with increase in temperature, whereas resistivity decreases with increase in temperature. So in short, properties of semiconductor: electrical conductivity, of course, is less than insulators and more than conductors. They exhibit negative temperature coefficient as the resistance decreases with increase in temperature and vice versa. The conductivity of semiconductors or its conducting properties can be changed by adding suitable impurity like gallium, arsenic. They can be changed appreciably. The properties can be changed. So impurities are added to create the different types of semiconductors. Of course, semiconductors, as we know, they have 4 electrons in the outermost orbit. They are classified as intrinsic semiconductors or pure type semiconductors since no impurity is added and they exist in their pure form. Extrinsic semiconductors, they are also called impure semiconductors. By adding suitable impurity, 2 different types of semiconductors are created. One is called N-type semiconductor and the other is called a P-type semiconductor. Let's see intrinsic semiconductor. So a semiconductor in its extremely pure form with no presence of impurity is called an intrinsic semiconductor. Here you can see all the atoms in the crystalline structure are silicon atoms. No impurity atom has been added. This is the central silicon atom and it is forming covalent bonds with the neighboring silicon atoms. So this is an example of intrinsic semiconductor. Extrinsic semiconductor, also called impurity semiconductors. So semiconductors in which impurities are added to increase the conducting properties. And the process of adding impurities is called doping. For germanium, the impurity level is less than 1 part impurity in 10 raised to power 8 parts of semiconductor material. Whereas for silicon, it is less than 1 part impurity to 10 raised to the power 12 parts of semiconductor material. Of course, purpose of adding impurity is either to increase the number of free electrons or the number of holes. So depending upon the type of impurity, we will have two different types of semiconductors. If a pentavalent impurity, that is impurity which has 5 electrons in its outermost orbit, is added, then a large number of free electrons will be produced in the semiconductor. And if a trivalent impurity which has 3 electrons in its outermost orbit is added, it will create a trivalent, we can say a p-type semiconductor. So let's see the two types of semiconductors depending upon the type of impurity which is added. So we have the N-type semiconductor and the other is a p-type semiconductor. Here you can see an impurity atom which has 5 electrons in its outermost orbit. So the central atom, impurity atom, is forming 4 covalent bonds with the neighboring 4 silicon atoms, and for each atom of impurity it will contribute 1 free electron. So this, since it is contributing 1 free electron, it is also called a donor impurity. Another, here you can see the central atom is an impurity atom, boron, which has 3 electrons in its outermost orbit. So it is forming 3 covalent bonds with its neighboring silicon atoms, and here 1 bond is incomplete. It is showing absence of electron since it has only 3 electrons in its outermost orbit. So absence of electron creates a hole. Since it is ready to accept an electron, it is called an acceptor impurity. N-type semiconductor, these impurities are called donor impurities. So when a small amount of pentavalent impurity is added to a pure semiconductor, it creates an N-type semiconductor. Good examples are arsenic and antimony. Arsenic, atomic number 33, and for antimony, it is atomic number 51. So 2, 8, 18. It becomes 28 plus 5 electrons in its outermost orbit. So similarly for antimony also, there will be 5 electrons in its outermost orbit. Such impurity atoms, since they are donating free electrons, they are called donor impurities. 4 electrons of the impurity atoms will form 4 covalent bonds. We have just seen with the neighboring silicon atoms, and each impurity atom will contribute 1 free electron. And so the result is the creation of an N-type semiconductor. Since the number of free electrons provided by the pentavalent impurity far more exceeds the number of holes. We know that free electrons are also created due to the thermal energy and covalent bonds break. So free electrons and holes are created. And in case of N-type semiconductor, there is a predominance of free electrons compared to the holes. Hence it is called an N-type semiconductor, where N stands for negative. Here you can see the structure for N-type semiconductor. This is the phosphorus atom, which has 5 electrons. 2, 8, since the atomic number is 15, 5 electrons in its outermost orbit. So the central phosphorus impurity atom is forming 4 covalent bonds with the neighboring 4 silicon atoms, and it will contribute 1 free electron. So for every phosphorus atom which is added as impurity in the semiconductor crystal, it will contribute 1 free electron, and this free electron is free to move in the crystalline structure. And this is the process of N-type doping. A p-type semiconductor is called an acceptor impurity semiconductor. Acceptor impurity, the impurity which is added, and a p-type semiconductor is created by the addition of a trivalent impurity. Examples are a gallium atomic number 31, indium atomic number 49, and boron atomic number 5. Gallium, so 2, 8, 18, and 3 electrons in its outermost orbit. Similarly for indium also, there will be 3 electrons in its outermost orbit. Such impurities which produce p-type semiconductors, they are called acceptor impurities because the holes created can accept the free electrons. 3 of the impurities electrons will form 3 covalent bonds with the surrounding silicon atom, and it will create 1 hole which indicates absence of electron. A small amount of gallium impurity provides millions of holes. So number of holes outnumber the number of electrons. Why? Because of course holes electrons are created by the In case of p-type semiconductor also by the breaking of the covalent bonds. But the number of holes far more exceeds the number of electrons. We can say there will be a predominance of holes in p-type semiconductor compared to electrons. Hence, it is called a p-type semiconductor, or P, where P stands for positive. This is the structure for a p-type semiconductor. Here you can see a boron atom which has 3 electrons in its outermost orbit. 2 and 3 contribute to the atomic number 5. So it will form 3 covalent bonds with the 3 silicon atoms, neighboring atoms, and it will contribute 1 hole. Hole is absence of electron. So for every boron atom, 1 hole will be created. And this type of doping is called p-type doping. This is a small comparison between the two intrinsic and extrinsic semiconductors. Semiconductors, of course, in the purest form are known as intrinsic semiconductors, and those are created by mixing of impurities are called extrinsic semiconductors. The conductivity of intrinsic semiconductors is low, whereas for the conductivity is quite high in case of extrinsic semiconductors. Electrical conductivity, of course, is a function of temperature alone in case of intrinsic semiconductors, whereas it is a function of both impurities as well as impurity atoms doped in the structure as well as temperature. The number of free electrons in the conduction band is equal to the number of holes in the valence band. Here, this is not the case. Number of free electrons and number of holes are unequal. These are not used practically, intrinsic, whereas these are used. And the Fermi level lies in the middle of the valence and conduction band in case of intrinsic semiconductor, whereas it is shifted towards the valence band or towards the conduction band in case of extrinsic semiconductors. Here you can see the Fermi level has shifted to the top of the valence band here, and here it is at the bottom of the conduction band. So this is n-type semiconductor, since the number of free electrons exceeds the number of holes. Here the number of valence, here the number of we can say holes far more exceeds the number of free electrons. So here is a small quiz for you to solve. Which of the following could be used as a donor atom used to produce n-type semiconductor material? Aluminium, boron, phosphorus, germanium. Yes, you can surely answer, since n-type semiconductor means pentavalent impurity, that is phosphorus. A semiconductor has dash temperature coefficient of resistance. Of course, it exhibits negative temperature coefficient of resistance. A semiconductor has generally 4 valence electrons in its outermost orbit. Addition of trivalent impurity to a semiconductor creates what? Many free holes or electrons? Of course, it is holes, since it is trivalent impurity. And the process of adding impurities is called doping. So, thank you.